Right, welcome to the end of the chapter 16 stuff. More complicated questions, more interpretation, a bit of the calculus, some travel graphs, more fun. Okay, so they introduce an idea we've already been using, the idea being an object is instantaneously at rest or changes direction when v is 0. They've said it reaches maximum minimum velocity when a is 0. The thing I want us to be careful about there is, yes, remember if you're looking for a maximum or a minimum, you have to check that you haven't found the other one of the pair. And also, finding a stationary value isn't always what you're looking for. Take this graph, for instance. In the first 5 seconds, we go from here to here. That's the first 5 seconds. And we see that there is only one stationary value. There is a stationary value here, but that gives a velocity of -3. The maximum velocity in the first 5 seconds is actually this value here. Okay, so yes, if you're asked for a maximum minimum velocity, by all means find a differential, but far better would be, once you've done that, consider the shape of the graph and see if what you found makes sense. Let's have a look at the... Right, if you want to read this example first, you can pause it while you're reading it. Right, find the time when the boat changes direction. The boat will change direction when the velocity goes from positive to negative, or negative to positive. So now in this case, the velocity was positive at the beginning, so we are looking for when it changes direction, when it goes from positive to negative. To find the velocity, we integrate the acceleration, and we get this. We substitute those values in, and we find that c is 4, which gives us this quadratic. Okay, you can solve that on your calculators, but you should be able to solve it without calculators for questions asked that. Get 2 answers. The negative one, these are times, the negative one isn't appropriate because we've got the motion starting at t equals 0, so we get v equals 4.3. For those who like different methods, we have this one here, which is possibly a bit pale for me to highlight, so instead I'm going to go over in yellow. We could start with the idea that dv dt is 12 takes 6t, which means we can then integrate both sides with respect to t and use limits. So we've got, if we integrate dv dt with respect to t, we're going to get a lovely result where that collapses down to an integrate with respect to v. We can integrate that side with respect to, we can integrate this side with respect to t. We get 12t take 3t squared. If you integrate the one which is there, you get v. Now the beautiful thing about this method is you can use limits. We can have limits where v is 4 goes with t is 0, and then we can use v and t, the variables, as the upper limits, and all that does is it gives us exactly the same result but without using the c. Does it save any time? No, not really, but it's just a nice sometimes to see a different method. You can probably forget that if you like integrating and finding constant integration. What's the maximum velocity of the boat? Well, the velocity this time is a quadratic with the coefficient of t squared less than 0, so we know that the stationary value is a maximum. Okay, we know that. So dv dt, acceleration is 0 when t is 2, which you sub that back into the velocity, gets 60 minutes a second. If you forget that it's a quadratic and you forget that you actually know the shape of a quadratic, by all means find the second differential. Now if you differentiate velocity, if you differentiate velocity twice, if you differentiate the acceleration once, if you differentiate this once with respect to t, you get -6, which is always negative. As in, that differential acceleration is always negative. So when t is 2, it is definitively negative, which means t equals 2 is a maximum. But we knew that from the shape of a quadratic graph. That leaves us with part C. At what time does the boat pass the rock again? Well, that's when s is 0. This is the integral of v with respect to t. If you integrate that, I'd use a different letter for the constant. When to get back to the starting point? So it's defined, the starting point is when s is 0. So s is 0 and t is 0 gives a constant of 0, gives us that quadratic. When is s 0? You can solve that. Oh, and that nicely is a cubic. But notice each term has a t in it. So you can factorize t out. Then you can solve the quadratic. So we get t is 0. And the quadratic gives us those two solutions. T is 0 corresponds to the initial time. That's when it started there at the beginning. T is plus 6.6 is the appropriate answer. And notice if you want to see it done, there's a way of generating the displacement equation using an integration with a definite integral with limits, if you want to do it that way. Right, the second example, if you want to pause it and read it, we've got the velocity defined in two different ways depending what the time is. We've got a quadratic for the first period of time, 14t take 5t squared, and for the second period of time we've got proportional to 1 over t squared with an addition of a 13. Find the displacement of the car from the parking space when t is 2, t is 5. Should simply be a case of substituting in and checking consistency. So when t is 2, change in displacement from the starting point will give us the final displacement. Integrate, definite integral, 14.7. Your calculators have a button that will do that for you, whether you've got the Class Whiz or the CG50. The change in displacement from 2 to 5 seconds, because remember the rule that's defining velocity changes after 2 seconds. So the change in displacement from 2 to 5 seconds is given by this, with limits of 5 and 2 this time, not 0. 2 and 5. That's 33. How far was it from the parking space? How far was it from the original parking space? Add your two answers together now. 14.7 after 2 seconds, another 33 after another 3 seconds. At what time is the car 35 meters from the parking space? Right. So for between 0 and 2, we know that this expression is never 0. Okay? We can check that by sketching the graph. So therefore the velocity is greater than 0 for the first 2 seconds. Why have I worked that out? What I wanted to check was that the car hadn't travelled out from the parking space and then come back again during the first 2 seconds. I wanted to check that this 14.7 here is the furthest it gets in the first 2 seconds. What I wanted to do is I wanted to rule out 35 meters being an answer for the first 2 seconds. So when s is 35, okay, the integral between 2 and t for the second wave of velocity is defined. That added to 14.7 is 35. If I take the 14.7 from the 35, I get that. And there, I haven't done this perhaps as neatly as I could have done. That integrates to give that. If you substitute the capital T and the 2 into that, you get that and that. Combine the number terms together, then multiply through by t, and you've got a quadratic. There are two answers. One's in the first 2 seconds, which we've ruled out as being an answer. So the valid answer is the 3.9. That one is another example of a good thinking one for these final bits of the chapter. Okay, so is the last example. So it's another one where the velocity is defined up to 6 seconds, and then the velocity changes after 6 seconds. Now notice in this case, both the expressions for velocity are linear. So if we are finding the area under the curve, it might be easier not to integrate because the area under the curve will be that of a trapezium or a triangle. Okay, you can do it by integration. You can check the answers in the book. You can check by doing it by integration. I've not done it by integration. So both linear. So the graph looks like this. For the first 6 seconds, we've got linear increasing. After 6 seconds, we've got linear decreasing. Find the displacement when t is 10. When t is 10, I've worked out the area under the graph. I've worked out area 1, which is a trapezium. And I've worked out area 2, which is a trapezium. The only thing I needed was the height here, which you can put 6 into either of the equations, check they match, and then I wanted the height here. So I put t equals 10 into the second one. And that nicely gives 137 meters. Question B, the maximum displacement of the particle from P. Right, some thinking again. Whilst V is 0, the displacement is increasing, okay? So, whilst the displacement is increasing, it's moving away. At the point where V is 0, it'll start coming back again, okay? So, V is 0 when this is 0. So V is 0 when that is 0 at 16.5. So the area under the graph from 0 to 16.5, and remember, for all of those first 16.5 seconds, the velocity is positive, so it's moving away. It might be slowing down from 6 seconds onwards, but it's still moving away before it comes to a halt. 75.6 was the first area, and now we've got the area of a triangle, which gives that. Okay. The displacement of point Q from P is 90. How long does it take for the particle? When does it first get there? How long does it take to return to there? So at 6 seconds, we knew it was at 75.6, and it had always been moving away from the origin. So we want to find out when it's 90 meters from point P, we want to know when the change of displacement in the second time interval is 14.4. Okay. Now remember, at 16.5 seconds, the particle came to a stop and then started coming back again. So if it had passed 90 meters, carried on, stopped, and come back again, it's going to come past 90 meters twice. So in this case, you could do it working with trapezia, but notice the height of the trapezium and the width of the trapezium both depend on t. So in this case, it's pretty easy to do an integration. When is the integral in the second time interval from 6 upwards equal to 14.4? If you integrate 29.7, take 1.8t, you get that. If you use these two limits, you get this quadratic to solve. If I turn my face off, I can speak, but I think my face appears on the thing still. You'll find that there are two answers. One's 6.79 seconds, one's 26.2 seconds. The 6.79 Now notice in the question, everything was to 2 or 3 sig fig. So it's not appropriate really to have 3 sig fig now. So 6.8, the first answer is when it first reaches 90 meters. The second answer when you solve this quadratic of 26.2 is the time it comes back to the origin. It comes back to 90 meters again. Right. Now, if you want to play about with something crazy on your calculator, you could find the solve n button and you could type in the integral being equal to 14.4, then do a comma. If you call what we're trying to find, give that a letter, after that comma you put a letter, the thing you're solving for, then a comma, and then what you can't see under my face is a 0, where to start looking, a comma, and then I've done up to 30. Up to 30, and then I've closed the brackets and pressed equal. That, if you play about with that, will solve any equation, including definite integrals. Right, what I would recommend you do, we've looked at chapter 16 and chapter 17 now, 2 big chapters. I would create a checklist of understanding for those, okay? You could go onto the online textbook, take all the key points we've been looking at, take the PowerPoints we've been doing, and get a checklist for chapter 16, which introduced kinematics. Then we did the Suvat equations in chapter 17, which we applied to projectile motion, and then we applied to the multi-stage problems, and then we've come back to the calculus and the travel graphs. It's all brilliant and important. 16E is a really good selection on the questions on the problem solving. Okay, we used the second lesson this week to look at the mixed practice questions from 16 and 17. Okay, and that'll be the end of the second week after we've come back from the Easter break, and which by now we might be finding out when we might be coming back to school again. Good luck with those. Stay safe.